In the previous lectures, we have been talking about vectors, tensors, covectors, etc. in the abstract, more or less. From this lecture onwards, we are going to be a bit more concrete and deal with things which have direct applications to physics. Today's lecture is going to be sort of a warm-up lecture because we are going to talk primarily about three-dimensional vectors and tensors, which are sort of familiar things. But let us treat this more as a stepping stone towards four vectors and vectors and tensors under general coordinate transformations, which are going to be discussed in the rest of the course. The next lecture will be focused on the concept of four vectors, covectors, and tensors. In other words, objects that will be very important in the mathematical structure of the special theory of relativity in particular. If you have followed the previous lectures in this series, most of the concepts that I talk about will be rather familiar and easy to follow. In case you are coming here without having heard the previous lectures, I will try to explain some of the background. So there may be some repetition in this particular lecture for those of you who have heard the previous ones. To them, I apologize. But anyway, some of these concepts are important enough that they bear repetition. And just on the off chance that somebody is here who has not gone through the previous videos, I would like to give you some basic motivation in this lecture in terms of things which are more familiar, that is, in terms of what are called three vectors or vectors under rotations and three tensors as well. As we have explained over and over again in the previous lectures, the notion of covectors doesn't really make sense when we talk about transformations under rotations, simply because there is only one kind of transformation law for vector-like objects as long as we are sticking to orthogonal transformations. So a quick reminder, basically a vector is something which is modeled on the position vector, the vector with components x, y, z. Under the coordinate transformation, this vector transforms to a new vector, or rather, what we really should say is that the vector stays the same, but the components, the numbers that are used to describe the vector changes to x prime, y prime, z prime, and this new vector can be found out from the old column vector by the application of a 3x3 matrix called R. R is not just any 3x3 matrix, it has a special property. It's an orthogonal matrix, which means that R transpose is the same as R inverse. Now this has very important consequences. In particular, one of those important consequences is the fact that we do not encounter the concept of a covector in the world of three-dimensional vectors, at least in the world of vectors under rotations. And that is simply because the transformation rule for covectors is exactly the same as the transformation rule for vectors if your transformation happens to be an orthogonal. Now, I said that vectors are modeled on the position vector. And what this really means is that for any vector A which has three components, let's say AX, AY and AZ, under a coordinate transformation, these components will all change. Once again, let me emphasize that the vector stays the same. It's actually the components or the numbers which describe the vector that change. And these new components are related to the old ones in exactly the same way as the new coordinates are related to the old coordinates. That is, there is a matrix R which acts on AX, AY, AZ to give you AX prime, AY prime, AZ prime. And this matrix R is exactly the same as the one which transforms the coordinates. Just to set the stage for covectors that are going to be important when we talk about four-dimensional vectors later, covectors essentially transform in a slightly different way A covector omega would be described by three numbers just like a vector, but it would transform to omega prime given by R transpose inverse acting on omega. This rather complicated looking rule actually holds because we are trying to think of omega as a column vector, just like we thought of the vector A as a column vector before. But if we think of omega as a row vector, that is the transpose of this particular omega, then the transformation rule will be a simpler one, that is omega prime will be omega times R inverse. So in a sense, a covector transforms in exactly the opposite manner as a vector does. The reason why we did not talk about covectors in the world of 3D vectors is that rotation being orthogonal, R transpose inverse was exactly the same as R. Let me now quickly run through some examples of vectors. The first example is the obvious one, the position vector itself. After all vectors are modeled on the position vector, as we have just said. So the position vector is the prototype of all vectors, and that of course is our first example. The next one, the most obvious choice would be the derivative of r with respect to t, that is velocity. This is also a very familiar vector, so of course is the derivative of v dv dt, which is a, and then we have force, which is related to the acceleration via F equal to ma, and multiplication of a vector by a scalar leaves to the vector. That's rather easy to check from the definition that we quoted a while ago. And that means that both sides of this equation, the famous second law of Newton, happens to be vectors. Now let me just go back to velocity for a while and point out one thing. It seems rather obvious that velocity is a vector, but let us still take a look at why it is a vector. This differentiation is nothing but a limiting operation. You take the limit as delta t goes to 0 of the quantity delta r vector divided by delta t. This of course is a proper division. You take a finite non-zero time interval, find out how much the particle has moved or been displaced in that time interval, divide the displacement vector by delta t. Now delta t happens to be a scalar under rotations. In other words, if you rotate your coordinate system, delta t does not change because time does not change when you rotate your coordinate system. So, what you are doing here is multiplying delta r, a quantity which transforms like vectors, by 1 over delta t, a quantity which does not change when you rotate your coordinate system, which is why delta r vector by delta t transforms exactly the same way that delta r does. This division by delta t or multiplication by 1 over delta t does not change the transformation rule in any way. As a result, this thing is also a vector for all values of delta t, and hence its limit as delta t goes to 0 is also a vector. Now the critical thing here is this. Velocity is a vector because position is a vector. However, there is one critical ingredient in this statement, which is time is a scalar. It does not change when you rotate your coordinate system. Now this is going to be critically important when we go on to talk about Lorentz transformations, because as you all know, under the Lorentz transformation, the time as observed by an observer changes from the value as measured by another observer, and so it's no longer a scalar. So division by delta t will actually change the transformation properties of an object. We will have to take care of this fact when we define things like 4 velocities or 4 accelerations. Now, one important point that we can make immediately about this equation, Newton's second law, is that if you were to rotate your coordinate system, both the left-hand side and the right-hand side will change. Or rather, once again, the vectors will not change, but the components, the numbers that you use, they will change. But because they are both vectors, both the left hand side and the right hand side are vectors, they will change in exactly the same way. So this equation stays equally valid in the new rotated frame as it was in the original frame, not because the equation is invariant, not because it doesn't change, but because it is covariant. Both sides of the equation change, but they co-vary. They change identically. So this is an example of rotationally covariant equation. In fact, it is very easy to see that whenever we write an equation as an equality between two vectors, we are immediately going to get a rotationally covariant equation. This rotational covariance of vector equations is something that we have all used from very early on. For example, we have chosen a coordinate system which would suit our particular problem. Maybe we have chosen the x-axis as horizontal and the y-axis as vertical. But often, depending on your problem, you may have chosen an x-axis in an entirely different direction. Such a choice works because the underlying equations, being vector equations, are equally valid in all frames. Just to give you another slightly more advanced example, most of you would recall a proof of this famous vector identity that A cross with B cross C is B times A dot C minus C times A dot B. There are many different ways of proving this identity, but one proof would simply involve directly calculating both sides using components. But just doing that directly is a bit, clumsy and time consuming. What we often do is we choose a special set of coordinates. For example, we may choose a coordinate in which A is along the x-axis. Then we can no longer say that B will be along the y-axis simply because the y-axis by its nature is perpendicular to the x-axis and B may not be perpendicular to A, but B could be chosen to be in the xy plane. And C could be taken as a vector which has all three non-zero components. That leads us to a considerably simpler calculation of both the left hand side and the right hand side. But the important thing is, once we have verified our identity for this particular special case, we do not have to verify it for the general situation at all. This being a vector equation, if it is correct in one coordinate system, it is correct in all rotated coordinate systems simply because of the covariance. Both sides involve vectors and they both transform identically. So both sides change, but they change identically. So the equation, once true in one frame, stays true in another frame. Talking about the vector triple product reminded me that there are several physical quantities which are known as vectors, which are actually cross products of two known vectors. For example, the angular momentum L is simply the cross product between the vector R and the vector m times v, the momentum. And say the torque is a cross product between the position vector and the force acting on the particle. So these are vectors basically because the cross product of two vectors is a vector. Come to think about it, I have really not proven this in any of the earlier lectures on this series. So let me just take some time out and talk about why is the cross product a vector. Well, the cross product of two vectors, A and B, has an ith component which is given by epsilon ijk aj times bk. I am sure most of you already know this. Epsilon ijk is the completely antisymmetric symbol in three indices, also known as a Levi-Civita symbol, its value is 1 when I, j and k are 1, 2 and 3 respectively, and the fact that it is completely antisymmetric completely determines its value for all other index combinations. For example, epsilon 2, 3, 1 can be obtained from epsilon 1, 2, 3 by interchanging the indices twice. That is, if you interchange the first two indices here, you will get epsilon 3, 2, 1 because of the complete antisymmetry that's going to bring in a minus sign. And then by interchanging the 1 and 3, you are going to get epsilon 1, 2, 3, which we already know is plus 1. And because you have another minus sign because of the interchange, the two minuses give you a plus, so you get epsilon 2, 3, 1 also as plus 1. By the same token, you can easily check that epsilon 1, 3, 1, 2 is also plus 1, and epsilon 1, 3, 2, for example, is minus 1, obviously because 2 and 3 have been interchanged once. Also, any situation where two indices are repeated, you are going to get 0 simply because interchanging these two would not change the symbol, yet must bring in a minus sign because of the complete antisymmetry that we have posited, and so this must be 0. One more thing I have slipped in here without mentioning, but this should be very familiar to all of you who have heard the previous lectures and should be familiar to the rest of you as well. This is the so-called Einstein summation convention, which is simply that indices are summed over if they are repeated. So here the k index and the j index are repeated. So this really is a sum over all values of j and all values of k. Now, using this value for the ith component of the cross product, let us try to figure out what this is going to be once we rotate our coordinate system. So, what is A cross B's primed version? What is the ith component of that? That, of course, will be epsilon I, j, k, aj prime, bk prime. But we know that aj and bk are components of vectors, so this one essentially is rja. Let's call this p so that we don't confuse it with the letter a here, ap, and rkq, bq. So what we have is epsilon ijk, rjp, rkq, apbq. Of course, all the repeated indices j, k, p and q are summed up over here, and this switch in the order that we have carried out in this last step is more than just switching the order of two numbers in a multiplication. We are also implying a change in the order in which the summation is being done. In the last line, the summation is actually being done over j and k first, and the result is then going to be summed over p and q. Now, in order to ensure that A cross B really is a vector, we would need its ith component in the new coordinate frame, A cross B prime I, to be related to the old components by A cross B prime I is Rim, A cross B's mth component. Of course, summed over m. What we have is A cross B prime I is epsilon ijk rjp rkq times apbq, and it does not really look at this stage to be the same as what we are claiming here. In order to see that these two expressions are actually the same, what we need to do is take a look at this quantity first. Epsilon ijk rim rjp rkq. Of course, here I, j and k are summed over. You can only talk about specific values of m, p and q. In other words, I, j, k are dummy indices, m, p and q are free indices. Now let's just imagine that we have interchanged two of these free indices. Let's just say m and p. So the expression becomes epsilon ijk r ip rjm rkq. So only m and p have been interchanged. Note that I, j and k are dummy indices as we have mentioned. So you can rename them to be anything you want. After all, they are not indices which indicate a particular value. They are summed up over all possible values. So in particular, what we can do is change I to j and j to I. So this expression can also be written as epsilon jik rjp rim rkq. Now note that this is related to the original expression in a very simple fashion. RJP, RIM, this product is of course the same as RIM, RJP. These are just ordinary numbers, they commute with each other. What order you write them in does not matter. So this times this is the same as this times this. However, the epsilon symbol in front has changed because it's now epsilon jik, whereas it was epsilon ijk in the original expression. So what has happened is that you have picked up an extra minus sign. So these two expressions have an extra minus sign between them. So anytime you interchange any of the free indices in this expression, it changes sign. Now that should of course remind you of something. None other than the epsilon symbol itself that has this property, and it's very easy to see that this implies that this has to be of the form epsilon mpq times some number. The question is, what exactly is that number? And in order to see that, all we have to do is choose a particular set of values for m, p and q. In particular, let's choose 1, 2 and 3. Remember the complete antisymmetry that we have shown just now, that interchanging any two free indices changes the sign of this object, immediately implies that if any of the two free indices are equal, this expression is going to vanish. And if you know its value for 1, 2 and 3, you actually know its value for everything. So all you need to focus on is this particular number, epsilon ijk ri1 rj2 rk3. For this particular choice of m, p and q, the epsilon is going to be 1, so it's whatever this object is. Now what exactly is this? Notice that the fact that the 3 second indices here are 1, 2 and 3 says that we are taking one element from the first column, another element from the second column, and yet another element from the third column. So 3 indices from 3 different columns. Because of the epsilon ijk in front, the I, j and k are going to have to be different in order that a term contributes to this sum. That essentially means that we are taking elements from distinct rows and distinct columns, no two rows or columns being repeated, and they are being multiplied together. But they are also being multiplied in a particular manner. You are going to multiply R11, R22, R33, this expression exactly with I equals 1, j equals 2, k equals 3 with a plus 1 factor because epsilon 1, 2, 3 is 1. But you are going to take, for example, R21, R12, R33 with a minus sign, simply because here I is 2, j is 1, k is 3 and epsilon 2, 1, 3 is minus 1. Continuing in this fashion, you will see that there are 6 terms which are non-zero in this sum, and the sum should be very familiar to all of you. Once you expand this out, you should be able to recognize what this sum is. In fact, you should have been able to recognize this just from this description, that you are taking elements from different rows and different columns and multiplying them together and putting in plus 1 or minus 1 in the front. depending on a permutation of ijk, the row index. This is nothing other than the familiar number related to the matrix, the determinant. So, this is exactly what epsilon ijk, rim, rjp, rkq is. It's epsilon mpq times det r. But now comes the important point. For rotations, determinant of r is always plus 1. So as far as rotation matrices are concerned, this quantity is just epsilon mpq. So epsilon ijk, rjp, rkq times rim is epsilon mpq. In order to figure out what this coefficient epsilon ijk, rjp, rkq actually is, we start from this and just notice that apart from the rjp, rkq, epsilon ijk, this has one extra coefficient rim in which the index m is still free. And I exploit that by contracting that m with an additional term rlm. Notice that m being a free index, at least until this point m was a free index, that allows us to multiply this by RLM and sum up over all values of m. Of course, you have to do it on both sides. So, this is how it goes. But now you notice that RIM, RLM, this quantity, is actually the ILth term, ILth element of RR transpose. And we already know that RR transpose is the identity, so this is delta IL. And using the fact that this and this together summed up over m gives you delta IL, we can then carry out the summation over I trivially. And all this does is replace every other I in this expression. In fact, there is only one other I in this expression, which is in the epsilon ijk, and you replace that by L. So in the end, what we have figured out is this. Epsilon ljk rjp rkq is epsilon mpq rlm. Now you might object that what you needed was epsilon ijk rjp rkq, but that's easily remedied. L is after all a free index, and as long as you change it consistently on both sides, that is, change both of these two L's into I, the equation will stay valid. So this is the coefficient that you wanted. So in the end, what we have found out is A cross B's ith component in the new coordinate system, A cross B prime I, which was epsilon ijk rjp rkq apbq, is this epsilon mpq rim times apbq. We then realize that epsilon mpq apbq is nothing but the mth coefficient or mth component of A cross B, and this is of course exactly the same as what we had here. So in the end of the day, what we have managed to show is that the cross product between two vectors does have components which transform in exactly the same manner as vector components do, which ultimately justifies our name vector product for the cross product. To sum up, the transformation rule for the components of a cross product gives you directly the fact that A cross B's ith component in the new frame is given by this expression, which, using the identity that we had derived a while ago, gives you this expression, and that finally gives you the transformation rule for vector components. But let me just remind you that we have started with the assumption that we are dealing with rotations, and that is determinant of R is 1. But if determinant of R had not been 1, we could have been dealing with other orthogonal transformations like reflections, where determinant of R is actually -1, then we could not possibly have written this. The general expression, which works both for rotations and reflections, involve a det R here. So strictly speaking, as long as we stick to rotations, components of a cross product transform under a coordinate transformation just like coordinates do. But if instead of just talking about a rotation, you talk about a more general orthogonal transformation, like one which involves reflections or the parity operation, you have an extra factor of det R in the transformation. Now, let me just point out that both reflections and rotations preserve lengths, so they are both orthogonal matrices, so they obey this, and for all orthogonal matrices, an immediate consequence is the determinant of R times the determinant of R transpose, which is square of the determinant of R, is equal to the determinant of identity, namely 1, and that means determinant of R for any orthogonal transformation has to be either +1 or -1. We have already said that for rotations it is +1, but for other improper orthogonal transformations, which means essentially combinations of rotations with reflections, you have a determinant of -1. Now this says something very interesting. What this is telling us is, as long as we stick to rotations and rotations alone, the way in which components of a cross product transforms is exactly like a vector. However, the moment you bring in reflections or parity, the way in which the components of a cross product of two vectors transform is actually opposite the way in which coordinates transform. Instead of having a single factor of RIM, you have RIM times -1. So, cross products of two vectors behave exactly like vectors when you carry out a rotation, but when you carry out a reflection, the cross product of two vectors behave exactly oppositely to the way a vector does. This is something which is familiar to all of you. This is behind the statement that the cross product of two vectors is a pseudo-vector, or what is often called an axial vector. So, vectors like L or omega or B are pseudo-vectors, where B is the magnetic field, of course, and this has immense ramifications on the use of symmetry principles in physics. If you are interested, you can take a look at one of my lectures on the use of symmetries in physics, where I discuss this issue about vectors versus pseudo-vectors in some detail. I will give the link in the comments below. For the time being, let us go back to the relationship that we used to derive the results just now. This relationship that you can see on your screen right now, which connects epsilon ijk rim rjp rkq to epsilon once again. Now, it should be pretty easy to see that you can rewrite this expression in the following form. Multiplied by epsilon mpq will actually turn out to be epsilon ijk. Actually, if you talk about non-rotations, where you have a determinant of R, this would give rise to an extra determinant of R on this side. So basically, you really have a 1 by det R. For the time being, let's not worry about this one, because we know that this is 1 for rotations. Now take a careful look at what this expression is telling you. If we were to pretend that what we have here is a third rank tensor with three indices, T, M, P, Q, whose values of whose components in a particular frame happens to be epsilon MPQ. Then if you carry out a rotation of coordinates, the ijkth component of the transformed tensor would of course be RIM, RJP, RKQ times T MPQ. This of course is epsilon MPQ according to our assumption, and this would turn out to be epsilon ijk from this formula. So what does this tell us? It tells us that if you had a third rank tensor whose components were equal to the values of the Levi-Civita symbol in one coordinate frame, then the components will be equal to the Levi-Civita symbol in all coordinate frames which you obtain by rotating the coordinate system. This is what we actually mean when we often say that the Levi-Civita symbol is a numerically invariant third rank tensor. Let me remind you that this is not entirely new to you. After all, delta ij, the delta symbol, is also of the same kind. It's a numerically invariant second rank tensor under rotations. Now this fact about the epsilon symbol being a numerically invariant third rank tensor fits rather nicely with the fact that AJBK is the outer product, or rather AJBK is a jkth component of the outer product of two vectors A and B, which by the way is a prototype for all second rank tensors. So what we have here is a third rank tensor multiplying the components of a second rank tensor term by term and summed up. This is exactly what we call contractions. So we have a third rank tensor contracted with a second rank tensor. And as we had learned before, when you do such a contraction, the resulting object has to be a first rank tensor. A quick way to see this would be to realize that the two indices j and k here are dummy, and therefore this object has only one free index, namely I. So this is really the ith component of a single index object. And from what we have learned earlier about contractions, this tells us that this is actually a legitimate first rank tensor, that is a vector. So the fact that the cross product of two vectors is actually a vector really relies on this rather advanced fact that the Levi-Civita symbol happens to be a numerically invariant third rank tensor, and what you have done here is that you have contracted this with the outer product of two vectors, which is a second rank tensor. That's rather a mouthful for a very familiar concept, that of a cross product, but that is really the way it is. Before we move on to four vectors and covectors, that is, we move on to the four-dimensional world of the Lorentz transformation, let us quickly take a look at what would happen in our 3D world if we moved away from rotations and talked about general linear transformations, that is, transformations which were not necessarily orthogonal. Now, as we had explained before, for non-orthogonal transformations, we have to distinguish between two different kinds of n-component objects, n being the dimensionality of the space that we are talking about, in this case, three-dimensional objects. There would be vectors which transform exactly the same way as coordinates, and on the other hand, there would be covectors, objects which transform differently. Now, in order to distinguish between these two, we have to use upstairs and downstairs indices, upstairs indices for vector components and downstairs indices or suffixes for covector components. So the relationship that we are going to write down for a transformation of coordinates becomes this: x upper I goes over to x prime upper I. This upper index is simply a way to write the index which helps us to distinguish it from covector indices. This has no connotation of a power. This has to be equal to s upper I lower j xj. The way in which we write these indices on S, the transformation matrix, is simply in order to be consistent with two basic rules. One is, once we go away from orthogonal transformations and we do have upstairs and downstairs indices, the summation convention is imposed when an index is repeated, but repeated once as a suffix and again as a superfix. That is why, because we had an x upper j, the j index in S, the column index for the matrix S, has to be a lower index. On the other hand, free indexes must match on both sides, both in their identity and in their location. Because you have an x prime I, an upper index on the left hand side, the ith index, the row index of S, has to be upstairs. Now, if we were to pretend that epsilon is a 3,0 tensor or a third rank contravariant tensor in the old language, then epsilon prime ijk would simply be an object which picks up three factors of S in its transformation. In other words, it would be what is written in blue: SIM, SJP, SKQ, epsilon, MPQ. Now we already know that this would have been exactly equal to epsilon ijk had the determinant of S been 1. But actually the determinant of S is not 1, and as a result, epsilon ijk would not have been numerically invariant if we had assumed that this is a third rank contravariant tensor or 3,0 tensor. What you need to ensure that we have a numerically invariant quantity is an extra factor of 1 over determinant of S in the transformation rule. So, for general coordinate transformations, epsilon ijk is not really a 3,0 tensor. It's actually a slightly more general quantity. This is called a tensor density. More formally, this is called a 3,0 tensor density with weight equal to -1. The -1 simply is a power of determinant of S which you have in front of the transformation rule. Determinant of S to the power -1. Now we will have more occasions to meet densities in later lectures. But at this point, let us focus on what the transformation rule would be for a quantity like this. The lower index version of epsilon, which is of course numerically exactly the same as the upper index version. So epsilon prime ijk, one might think, would of course transform with covector transformation coefficients, but would also have a factor in front, just like the upper index version. But what should that factor be? Just to understand that, let us take a look at what this really is. Remember, the S up lower I upper M is actually the imth element of S transpose inverse. And by following the same kind of argument that we used a while ago, it should be pretty easy to figure out that this quantity really is not epsilon ijk, but determinant of S transpose inverse times epsilon ijk. But determinant of S transpose inverse of course, is the same as 1 over determinant of S. So in order to ensure that epsilon lower ijk be numerically invariant, what you need to do is multiply this by an extra S. So this lower index version is actually a 0,3 tensor density with weight equal to +1. Now this actually has other consequences as well, which it so turns out we are already familiar with. For example, the cross product would really be something like this. AJBK, this would be the ith component of the cross product between two vectors. Actually, this would be the ith component with the lower index I of the corresponding covector. But if we are worrying only about orthogonal transformations, let's keep to that as of now, then the upper index or lower index versions actually have to agree. Now you might worry about what would happen with the Datus factor there. In the previous statement, we said that the upper index has a version as 1 over Datus and the lower index version has an extra Datus. That is, one had a weight of -1, the lower index version has a weight of +1. For orthogonal transformations, note that S transpose inverse is already the same as S, so the coefficients sitting in front, the S coefficients are all the same. What about the determinant? Well, the determinant for an orthogonal transformation is either +1 or -1. Remember, it's always +1 for a rotation, so it doesn't matter whether there is a Datus in the front or not. But if you include reflections, that is, if you consider all orthogonal transformations, then Datus could also be -1. However, if Datus were -1, then 1 by Datus and Datus to the power 1 are actually exactly the same, so it does not really matter in that case. So, if you move away from rotations but stick to just orthogonal transformations, we are completely free to use only lower indices, and there is no difference between the transformation rules for the upper index and the lower index version, even there. Now, one thing that will happen is that when you consider the transformation of this ith component, and we will only write things with lower indices for the time being because, as I said, it doesn't really matter as long as we are dealing with only orthogonal transformations. If you carried the thing through, you would easily see that the transformation rule for this actually works out to be Sij A cross B's jth component. Note that I am using S for the coordinate transformation. It may be a rotation, may be a rotation reflection. But in addition to this, because of the extra factor of Datus that is there in epsilon prime ijk, there's also a factor of Datus here. And what does this tell us? It tells us that a cross product of two vectors does not really transform like a vector under a general orthogonal transformation. Under rotations, of course, Datus is 1 and you cannot make out the difference between these two behaviors. However, if you are talking of general orthogonal transformations, what this extra factor of Datus does is that for rotations, cross product components transform exactly like vector components, but for reflections, you get an extra minus sign, that is, cross product components transform exactly oppositely to vector components. And that is what we have already learned about before, that the cross product of two vectors is not a vector under orthogonal transformations. It's a perfectly good vector under rotations, but under general orthogonal transformations, it happens to be a pseudo-vector or an actual vector. Let us now pay attention to the issue of the covariance or otherwise of a very important equation in physics which involves the cross product. I'm referring to the Lorentz force law. Force vector equals charge times E plus V cross B. In terms of components, what this translates to is Fi, the ith component of F, is Q times Ei plus epsilon ijk Vj Bk. The latter, of course, being the ith component of V cross B. Now, what happens to this equation when you carry out an orthogonal transformation? To begin with, let us examine what happens when you carry out a rotation. Then, Fi becomes F prime I, which is of course Q prime times E prime I plus epsilon prime ijk V prime j P prime k. So the question we have now is this equation the same equation as the original one? Or at least, even if the two sides have changed, which they have they changed identically? Now notice that F prime I is nothing but Rij Fj in terms of the old components of the force. What about Q prime? Charge is a scalar, so it doesn't change under rotation, so you just have Q. E prime I is obviously Rij Ej. Again, we have just used the basic property that electric field is a vector. Now what about this? Let me just do this in some detail, although we have already done all the steps before. There's no harm in repeating that. Epsilon prime ijk, remember, is a third rank tensor. So it will have a transformation rule Rim, Rjp, Rkq times epsilon mpq. I've left a gap here deliberately. We will come to this later. What about V prime j? V prime j, again, being a vector component, what we get is Rj small r Vr. This is pretty easy to write down. All we have to do is be careful that we are not confusing this dummy index with some other index we have already used before. And Bk, under rotations, behaves just like vector component, so we get Rk S ds. Now note that Rjp, Rjr involve the sum over j, and that really is the prth element of R transpose R. Rjp is the pjth element of R transpose. Rjr is a jrth element of R itself. So putting them together, this sum over j is actually the prth element of R transpose R, as I have said. And since R transpose R is the identity, this being an orthogonal transformation, this is really delta PR. So what we have is Rjp, Rjr go away, leaving a delta PR. And similarly, Rkq, Rks, they go away, leaving behind a delta Qs. Because of the presence of these delta symbols, it's very easy to sum this up. What you get is Q times Rij Ej, which you already had, plus Rim. Okay, maybe I will once again leave the space here. So plus Rim times delta PR. What that will do is change all the R's in the sum elsewhere to P's, and delta Qs will change all the S's to Q's. So we have epsilon mpq. Then we have Vp as a delta PR at work, Bq. And notice that because m is a dummy index, we could just as well replace m by any other dummy index, as long as I'm not confusing it with something else. And so what I get is Rij epsilon j pq Vp bq, Or, as can be easily seen, this is Rij times Q times Ej plus epsilon j. Well, in fact, I can write this as KL VKBL if I want. In either case, this is the jth component of V cross B. Because R is an invertible matrix, we can easily cancel out the Rij on both sides, and we see that the equation f prime I equals q prime e prime I plus epsilon prime ij k v prime j b prime k is exactly identical to the original equation fj is q times ej plus epsilon j k l v k b l. Now, why did I leave the little gap that I did before? The answer simply is that when we consider transformations which are not rotations but still orthogonal transformations, we have to remember that epsilon is really not a third rank tensor, it's a third rank tensor density. So there's an extra Détard factor in the epsilon transformation. But if that were really the case, then it seems like we are getting in trouble. Because of this presence of the extra det R, we no longer have the old equation equivalent to the new equation. The new equation f prime I equals this is actually equivalent to fj equals q aj plus Détard epsilon jkl vkbl, or for a reflection, this would become q times ej minus v cross b's jth component. So whereas the original equation was f vector is q into e plus v cross b, under an orthogonal transformation which is not a rotation, in particular an orthogonal transformation which is a reflection, f vector would become f q e minus v cross b. What this would seem to imply is that this law of physics, namely the Lorentz force law, which we have already shown is covariant under coordinate rotations, is not covariant under a more general orthogonal transformation. That is, it does not seem to be covariant under reflections. In other words, a charged particle in a mirror world would behave differently from a charged particle in our world. But that is not really correct. That is not correct because under orthogonal transformations in general, not necessarily rotations, we must remember that the magnetic field is not really a vector. It actually is a pseudo-vector. What that means is that the magnetic field will also pick up an extra factor of det R. And what this will do is that you will get a factor of det R whole square in the whole thing, and that is simply 1. The two det R's cancel each other. Indeed, under more general coordinate transformations, the two determinants would still cancel each other simply because one would involve a 1 by det R and the other would involve a det R. I will leave you to worry about why that happens. So, frankly, both in the mirror world and in the real world, the law stays exactly the same. So the Lorentz force law is actually covariant under general orthogonal transformations as well. The price that you have to pay for that, of course, is that B is no longer just a vector. B is actually a pseudo-vector. As long as you confined yourself to rotations alone, there was no difference. But for a general orthogonal transformation, there is a difference. Since we are talking about electric and magnetic fields, let me briefly discuss the issue of covariance of Maxwell's equations under rotations. Maxwell's equations, as you all know, involves the divergence and curl of the electric and magnetic fields in the differential form. We already know that E and B behave like vectors under rotations. Under general orthogonal transformations, of course, E and B behave slightly differently. E as a vector, B as a pseudo-vector. But for rotations, they both behave like vectors, and for the time being, let me focus on rotations alone. The real question here that will decide their covariance is what does del, the operator, behave like. Now, we have always called del a vector operator, and that actually has encouraged us to think of del dot E like it is a dot product of two vectors and hence a scalar, and del cross E like the cross product of two vectors and hence a vector. Now, if that were really correct, then you could see that for the two Maxwell's equations on the left, the two Gauss equations, the Gauss law for electric fields, which is actually Gauss's law, and its analogy, the Gauss law for magnetic fields, these both would involve scalars on both its sides, scalars and the rotations. So, when you rotate your coordinate system, both the left hand side and the right hand side stays invariant, so the equation does not change. On the other hand, if you look at Faraday's law here, or the Maxwell-Ampere law, which is the final of the four Maxwell equations, if del cross E really were a vector, then both sides of the equation would be vectors, and therefore both sides would covary, change equally when you rotate your coordinate system. At least if you were to write both sides down in terms of components, then the components would covary. Now, all that remains now is to check that the statement I have made right now, which we all take for granted somehow, that del is really a vector, or it sort of behaves like a vector, where does that come from? So let's check whether del really is a vector operator by looking at what happens to it when you transform your coordinates. So how exactly are the components of del prime related to the components of del? So the question really is, how is the ith component of del prime, del x prime I, related to the jth component of del, that is del xj? We all know the answer from elementary theory of partial differentiation. This is nothing but del xj del x prime I. So all we really need to do is figure out what this partial derivative is. Notice that x prime I, the new coordinates, are related to the old ones by the coordinate rotation matrix Rij xj. And then this also means that the old coordinates are related to the new ones by the inverse matrix here, and because of that we have ji xi prime I. So del xj del x prime I, this quantity sitting here, is nothing but the jith element of R inverse. But because we are dealing with orthogonal transformations, R inverse is R transpose. So this is the same as the ijth element of R. And so the transformation rule for the components of del becomes del x prime I is Rij del xj, which is exactly the same transformation rule as for a vector. Let me point out that at this stage, if we were dealing with general coordinate transformations, even non-orthogonal linear transformations, this would really not be the same transformation as for the coordinates. There would be a difference. We have already talked about that before. But for the time being, all we really need to worry about is under rotations, the way del transforms is exactly the same way as does a vector. In fact, that's true not only for rotations, it's true for all orthogonal transformations. And from that, it should be very trivial for you to show that the Maxwell equations are actually covariant equations under both rotations and reflections. Let me leave that as an exercise for all of you to work out. So the question really is, how is the ith component of del prime, del x prime I, related to the jth component of del, that is del xj? We all know the answer from elementary theory of partial differentiation. This is nothing but del xj del x prime I. So all we really need to do is figure out what this partial derivative is. Notice that x prime I, the new coordinates, are related to the old ones by the coordinate rotation matrix Rij xj. And then this also means that the old coordinates are related to the new ones by the inverse matrix here, and because of that we have ji xi prime I. So del xj del x prime I, this quantity sitting here, is nothing but the jith element of R inverse. But because we are dealing with orthogonal transformations, R inverse is R transpose. So this is the same as the ijth element of R. And so the transformation rule for the components of del becomes del x prime I is Rij del xj, which is exactly the same transformation rule as for a vector. Let me point out that at this stage, if we were dealing with general coordinate transformations, even non-orthogonal linear transformations, this would really not be the same transformation as for the coordinates. There would be a difference. We have already talked about that before. But for the time being, all we really need to worry about is under rotations, the way del transforms is exactly the same way as does a vector. In fact, that's true not only for rotations, it's true for all orthogonal transformations. And from that, it should be very trivial for you to show that the Maxwell equations are actually covariant equations under both rotations and reflections. Let me leave that as an exercise for all of you to work out. Bye for now.